All right, let's open up to page 93. We're going to take a look at our next section today, and continuing about our discussions in this first unit, like with graphical characteristics and function notations, we're going to take a look at another graphical property today, and that's specifically symmetry. Okay, some type of pattern or connectedness within a graph, if you want to think about it that way. So we're going to be discussing two different types of symmetry, and maybe you are familiar with them, maybe you're not. But we have what's called reflective symmetry, but also rotational symmetry. Now, symmetry, if you think about maybe artwork, is where things kind of are mirrored, where you have one image on the left and it would be the same image on the right, okay, where you have that reflection or mirror symmetry to it. So reflective symmetry in terms of a graph is a particular type of symmetry where if we have a line that can be drawn to fold the graph, and it, for lack of a better phrase, would land on itself. Okay. So if you think about your face, for instance, if you were to kind of draw a dotted line down your forehead, over your nose, over your lips, and you would take the right side of your face and fold it over to the left side, wouldn't your eye land on your other eye? Right? And then the one side of your mouth would land on the other side of your mouth. Like what's on the left side is the same as what's on the right. Okay, that's type of reflective symmetry, where we have that imaginary line that can be drawn and you can fold it. Okay, rotational symmetry is a little different. So instead of folding, we're literally rotating, okay, or like turning in a circle, if you will. So a rotational symmetry is a graph if it can be rotated 180 degrees and it looks exactly the same. So if you were to flip your paper or your graph upside down, okay, it would be the same image as if it were right side up, okay, normally. So we have two different types of symmetry, where we can have an imaginary line, where we can do some folding, or we can do some rotating for rotational. So we're going to just go ahead and try to classify these four graphs on that page as either reflective or rotational, and then we'll get a little bit more specific with those particular symmetries. So if you take a look at the first one, this one can be kind of tricky. If you were, and I don't know if you have it available on your paper if you want to take it out of your binder, notice how if you take a real good look at the way this graph is right now, if you were to flip it upside down, wouldn't it be exactly the same? It's the same shape. Okay, so this is what we would call rotational symmetry. Okay, if you were to flip it upside down, it would be exactly the same. So here's my question to you, if we can get a little bit more specific. If you were to flip it upside down, can you think about which of those kind of bolded points on the graph is staying stationary as you fold it? What do you think, Mike? The origin. Okay, so if you want to take a look at it again, notice how if I fold it upside down, the origin didn't really move. Okay, it's almost like I could put my finger there and rotate it, and notice how it would be exactly the same. Okay, so the origin is not moving when you go through this rotation. So sometimes this is what's referred to as origin symmetry, and kind of rightfully so, because the origin doesn't really move. It's almost like you put a thumbtack or your finger there and it stays still. Okay, so that's rotational, if you can move it upside down and it's exactly the same. What about this example of an absolute value graph that we kind of talked about in the last section? can we identify a particular type of symmetry? If you were to fold it some way, would it land on itself? Or if you were to flip it upside down, would it be exactly the same? Can we classify it as either reflective or rotational? What do you think, Mike?
It'd be reflective.
Reflective. Okay, so you're telling me if you classify it that way, that you have some imaginary line that you can fold it and it would line up on itself. Can you describe where that line might be?
It'd be over the y-axis.
Okay, so if you imagine that's where you would fold it, okay, kind of like a piece of paper. Notice how this left side, if you fold it over that line, would land up here. Okay, if you actually want to test it on your paper, you can. So if we can get a little bit more specific, we'll classify this as y-axis symmetry. So reflective is just the idea that we have a line that we can fold our graph. Okay, just a line. We can get a little bit more specific on where that line is. Okay, for this case, it was the y-axis. How about the one at the bottom? Can we fold it some way or rotate it? Can we classify the symmetry? What do you think, Pietro? Reflective, okay. So can you tell me where that line would be? How can we fold it? You want to keep going? Yeah.
It would be a line that has a slope of 1 and starts from the origin.
Okay, so kind of this perfectly diagonal line goes through the origin, slope of 1. I like that. Can we figure out the equation of that line? If it has a slope of 1 and goes through the origin. Y equals mx plus b? Yeah. Y equals x. Okay, so y equals x symmetry. So reflective was just the sole idea that we have a line somewhere where we can fold it, but then we can get a little bit more specific on what that line actually is. What about our last one? Can we fold it somehow or rotate it? Good, Alex?
Reflective.
Reflective. Okay, so where's that line?
Like this, like where it flips.
Mm-hmm.
That would be the x-axis.
The x-axis. Okay, so x-axis symmetry. A little side note about this x-axis symmetry idea. Would your graph pass the vertical line test? No, because if you have x-axis symmetry, you have a point up top as well as below that x-axis. So if it doesn't pass the vertical line test, what can we then conclude about any y-axis symmetry graph? Do you remember what the vertical line test tells us? Our conclusion? Yeah? It's not a function. Okay, so all x-axis symmetry graphs are not functions. So what we're going to spend a great deal of time in this section doing. Good morning. Anything for the office today? I think we're good. Thank you. So what we're going to spend a great deal of time in this section, actually the next section, doing is diving a little bit deeper into these different types of symmetries. So what are some more pinpoint characteristics that we can identify to help us determine if a graph is symmetric or not? Or what are some properties that are involved or related to these symmetries? So we're going to first take a look at the origin symmetry a little bit more closely. Okay, the one that I classified on the previous page. So we're going to take a look at this idea of origin symmetry and see, well, if we have a graph, how can we determine that it has origin symmetry? If we have a table of values, okay, that's what it means by numerically. You have some numbers or a table of values available for you. And then analytically means by hand, okay, some algebra. So using these three different representations that we might have, how can we reach this conclusion of origin symmetry? Okay, so graphically is kind of the easier one because that's what we did on the previous page. We said that if we were to rotate it 180 degrees, it would be exactly the same. Okay, but maybe we can get a little bit more specific with that. Notice how if we have points in the first quadrant and we rotated those points 180 degrees, can you determine where they would land? In which other quadrant would those points be in? Maybe I'll bold these. Okay, if I have points in the first quadrant and I flip my paper upside down, where are the points now located? In which quadrant? Do we know how to label our quadrants? One, two, three, four. Okay. And so if I flip it upside down, this is now quadrant, yeah? Three, okay? So notice how graphically maybe we can use some of these points to help us out. So we can say points in Q1 would land in Q3, okay, if we were to flip it 180 degrees. But that's just for this example. What if I had points in quadrant 2 and you were to flip it 180 degrees upside down? Where would those ones land? Yeah? Would land in quadrant 4. Okay, so not only can we just say 180 degrees, but we can get a little bit more specific, like where are the points located? And then if we do flip them, where would they then be? Okay, looking at that a little bit more intensely. So numerically, we're going to get into the actual numbers of the points. Okay, a little bit more specific even yet. So let's take a look at this first bolded point in our quadrant, our first quadrant. That ordered pair would be 2, 2. And if you were to flip that point 180 degrees, we said it would land in quadrant 3. It would most likely match up with this one, which has the ordered pair -2, -2. Maybe we can look at the other point as well. So the other point in the first quadrant was 4, 3. And if we flip it 180 degrees, it would land in the third quadrant. And it looks like that ordered pair is -4, -3. So if we take a look at the points even more closely, can we see another pattern? Do you see a connection between the points? And if you were to flip them, yeah? They become the opposite. Okay, so notice how if we start with a point, meaning an X and a Y, and we were to flip that point 180 degrees, it would then become a -X and a -Y. Okay, so there's a relationship between the points if we have origin symmetry. So numerically, meaning numbers, we can say the point X, Y becomes the point -X, -Y. Can we see that based off the graph? Okay. Analytically, we're going to write down something we're going to think about when we start to talk about the equations and how we can determine symmetry. This one might not be as obvious based off the graph, but we're going to write it down just for now, but come back to it most likely tomorrow, okay, just so we have it in our notes. So it's still related to this idea, though, that if we have a beginning point and it turns into this ending point, we want to show that connection. So just so we have it down for now, we're going to say the substitution, like plugging something in, okay, the substitution of the point -X, -Y would result in the same original equation. Again, I don't know if we'll have the time to actually get to that idea today, but we definitely will tomorrow. All right. let's dive a little bit deeper into the y-axis symmetry. So same example from the front. I think Mike told us that we had that imaginary line on the y-axis that we can fold, okay, and the points would match up. So graphically, okay, if we have y-axis symmetry, notice how the points on the right-hand side of the y-axis, if we were to fold them over, would land on the points on the left-hand side. So we can say right points from the y-axis fold over to the left points. Or vice versa, left points fold over to the right points. Again, I think that's a little simple for us because we have that visual. Okay, we have that picture. If we dive a little deeper into those points, okay, getting a little bit more specific than this general folding or matching idea, let's look at the numbers. So this first point has ordered pair 2, -1. If we fold it over, yeah?
Would it just be x of y becomes x, no, negative x in y?
Okay, so we're trying to find that connection. What are the values that are changing or becoming opposites? So for instance, if we start with this point on the right, which has the ordered pair 2, -1, and we fold it over that y-axis, okay, that imaginary dotted line, it would then become or match up with this point. So notice how the x value changed sign, but the y value stayed the same. So very similar to how we stated our point relationship for origin symmetry, we'll say something down here as well. So the point x comma y, okay, whatever x value you start with and whatever y value you start with becomes x comma negative y. Notice how other way around, negative x comma y. So the x's changed sign, but the y value stayed the same. Okay, if we can identify that numeric relationship, maybe within a table or on a graph, we then can conclude it has y-axis symmetry. Okay, maybe we don't have a picture to help us out with that. Okay, so we have the specific relationship between the points for this particular type of graphical symmetry. Again, analytically, we probably might not have time to get to this today, but we're just going to write it down, and it's going to be the same idea. Okay, just instead of negative x, negative y, because that was our origin relationship, we have this negative x, positive y. So we'll say if the substitution of the point negative x comma y would result in the same original equation. How are we doing so far? We're trying to identify specific relationships, okay, between ordered pairs or points to help us determine what type of symmetry we might possibly have. Okay, so whatever relationship we can identify, that's going to lead us to a particular type of symmetry. All right, let's try this y equals x symmetry, this diagonal line. Okay. So graphically, we could probably say something, I don't know, points above the y equals x line would land below. Okay. So for instance, this kind of top graph, if you fold it over, would then land below it. Or vice versa, you can start with the points below, fold it over, they'd land above. So it's not necessarily this left or right idea anymore. We kind of have this above or below idea. What about numerically? You see it? Yeah.
I don't know how to describe it, but basically it'd be like 0, 2 becomes 2, 0, and like vice versa, like the x and y kind of split.
I think you just said it right there. The x's and y's are going to flip. So if we take a look at the ordered pairs a little more closely, instead of just this above or below idea, maybe we can see some type of pattern. So if we start to label some of the points, okay, x's comma y's, notice how if we're folding it diagonally, okay, over this y equals x line, it looks like the x's and y's switch. So we can say, just so I'm consistent for what we said on the other ones, the point x comma y would become y comma x. Okay, we're flipping those ordered pairs. So if we can identify that relationship between the points on a graph or in a table, we then can conclude we have y equals x symmetry, okay, this diagonal line symmetry. Analytically, again, we'll get to it maybe tomorrow. We might have time today. If the substitution of the point y comma x would result in the same original equation. All right, last but not least, we'll have our x-axis symmetry, and this is the one that we said never was going to be a function because it would never pass that vertical line test. So graphically, points above the x-axis would land below, or vice versa, points below would land above. Can we find a numeric relationship, a number relationship between the points? If you were to take a point and fold it over, can we find a relationship? Yeah?
X negative y and x negative y.
X negative y. Okay, so let's see. This first point here would be 0, 2. And if we fold it over, it'd be 0, negative 2. If we look at another relationship, just to get another a pattern idea here, we'd have 6, 4, fold it over, 6, negative 4. So it looks like the point x, y, whatever point you want to start with, would become x, negative y. So the x stays the same, but notice how the y switches. So analytically by hand, we can say the substitution of the point x, negative y would result in the same original equation. Can we see those point relationships between all 4 different types of symmetry? They can get a little confusing because they all deal with x's and y's and they all deal with a negative somehow. It just depends on what's negative and what's changing. Okay? We went through that a little more quickly than I thought we were going to. Are we sure we're okay? All right. So we do have time to get to this analytically one. Okay, by hand using an equation. So on the next page, okay, we have 4 examples. We'll just take one at a time. We're going to try to determine if we just have an equation, what type of symmetry the graph would have. So even though we don't have the picture, and I don't know about you, but sometimes I don't feel like taking the time to actually graph these, okay, plot points and see what it would look like. Maybe we can use those point relationships to help us figure out the type of symmetry. Okay, how can we fold or rotate our graph? Okay, it'll give us an idea about what this graph might actually look like. So we had 4 different types of symmetry that we're going to have to test. Okay, the first one's going to be origin, and then we had the y-axis, the y equals x, and the x-axis. Because it actually is possible to have more than one type of symmetry. Maybe you have y-axis symmetry and origin symmetry. You're able to fold it but also rotate it, and it would be exactly the same. Okay, we're going to see if we have more than one type of symmetry. So with these 4 different types of symmetries, we need to remember or figure out what point are we actually testing to see if we can get out the same original equation. So can we reference if we have to, or maybe in our heads think about what were those ordered pairs? If you're able, for instance, for origin symmetry to rotate your graph 180 degrees and it's exactly the same, what would the ordered pair x comma y turn into? Yeah. Negative x, negative y. Okay, so that's the ordered pair we're going to test for origin. Let's see if we can actually do that. So in this original equation, we're going to substitute in a negative x for every x and a negative y for every y. So for this x, we'll plug in negative x, and for that y, we'll plug in negative y. We're interested in seeing if, when we simplify this, we end up getting the same original equation that we started with. Because if we do, we know that this origin point matches up with the other point, the regular x comma y point that you would pick, because they're going to be exactly the same. Okay, they would match up with each other. So can we simplify negative x squared? What's negative x times negative x? Yeah? X what? X squared. Okay? And if we simplify negative y squared, we'll get positive y squared. Okay? So take a look. After you simplify, do you get the same original equation? Yes. So without actually having a graph available to us, okay, this analytic or algebraic approach is basically showing or telling us that if we did have a graph, we'd be able to flip it upside down and it would be exactly the same. Because this origin point yields the same result as any other point would. Okay, let's see if it has x-axis symmetry with no graph. So we got to think about what is that special point we have to test. If you take a point on the right and fold it over to the left, what's that relationship? If you were to take x comma y and fold it over, what would it become? Maybe reference if you have to. Yeah? Negative xy. Okay. So we're going to plug that point in and see what happens. So for every x, we'll just plug in negative x. And since the y is not changing, okay, it's staying positive, we'll just leave the y variable the same. So like we said previously, negative x squared, if we simplified it, would change to a positive x squared. Do we get the same equation? Yeah. So not only does this graph have origin symmetry, okay, you can flip it upside down and it would be exactly the same, but you also have y-axis symmetry, meaning what's on the left and the right would match up, okay, if you fold it on the y-axis. So we have 2 different types of symmetry here. Let's check out if we have that diagonal symmetry, okay, that y equals x line. Can we think about what point we have to substitute in to test? Yeah. yx. Okay, so this one's a little different. Notice how for every x, we now need to substitute in a y variable because they switched. And vice versa, for every y, we have to substitute in an x. So if we rewrote the original, this would be y squared plus 2x squared equals 3. Do we get the same original equation? Unfortunately not, okay? So this graph, whatever it looks like, does not have that diagonal symmetry to it. Okay, they do not match up perfectly if you fold it across that line. Let's try x-axis. So what is that special point we have to test? Yeah?
X negative y?
X negative y. Okay, so the x is going to stay the same. Notice how we're not changing it. It's still, x is still positive. But the y value, we're going to substitute in a negative. And negative y squared would change to just a y squared. So do we get the same original equation? Yes. So this graph, whatever it looks like, I don't know, has origin symmetry. You can flip it upside down and it would be exactly the same. It also has y-axis symmetry. So what's on the left and the right would match up. It also has x-axis symmetry. So whatever's up top and below would fold over the x-axis and match up. So this is basically telling us it's not a function, right? Because if it has x-axis symmetry, there's no way it would pass the vertical line test. But without actually having a graph available to us, we are starting to think about what shape this might look like. Okay? We're going to stop there for today, but we're going to go ahead and test the other ones tomorrow. Maybe if you got the deal already or the gist already, you can start checking them out and see how you do. Okay? So we have 4 different types of symmetry that we're going to be focusing on for this section and the next one.